Again, then we got two really smart guys. I work at CarMax, so it's a little selfish. Get to support these guys from an architecture perspective. Sam and Yuri, wicked smart engineers working in our computer vision space at CarMax. They're going to show you this stuff at scale, what we do, how we do it. I think you got demos, and you guys aren't singing.
No singing. That would be bad.
Dancing only.
All right, cool. Guys, take it ahead. Everyone, big round of applause for Sam and Yuri.
Awesome. Thank you so much, y'all. Thanks for having us this year. So I'm Sam Gottlieb, joined with Yuri. We're going to talk to you today about computer vision innovations at scale and how we're doing that at CarMax. So first, just going to do a quick introduction of myself. So my name's Sam Gottlieb. I have a degree in computer engineering from Vanderbilt, and I've been with CarMax since 2019. And I'm currently an engineer on the computer vision team at CarMax. So I've been in the machine learning space since I joined CarMax in 2019. Previously, I worked in the Salesforce space. The machine learning space has been really great for me. It really ties me back to my computer engineering roots, where I specialized in hardware optimization, because I love working with big compute, big models. With computer vision specifically, right, we're using these big intensive models that we need to optimize to run at scale. So it's really bringing me back to my roots there. Outside of work, I love skiing, backpacking, and hiking.
All right. First of all, thank you for this opportunity. My name is Yuri, full-time associate at CarMax since 2020. I have a background in mathematics, computer science, electrical engineering. Currently, I'm an engineer on the computer vision team, and my interests are machine learning and computer vision. And today, we will take you through the journey of what does computer vision mean to us at CarMax. What capabilities do we provide to our teams? Because nothing is, you guys hear me okay? Nothing is in void, so there's a lot of people and teams involved in this process. And also, how do we do this at scale, at massive scale that we have? So we'll start with a brief history of computer vision at CarMax. So if you look at this screen, you can see the matter of things circa 2019. So yes, you see cars, but the experience is not what you wish for. You can see first of all, you can tell right away that the consistency is not the same. You can see some background, the colors are not the same. It just aesthetically does not look like it all belongs to the same place. What we're trying to do here is realize the challenges that we're facing. So at CarMax, we have over 200 locations. Each location has their own different managers. They have different training. They capture images differently, upload them differently. Also, we are ingesting about over 400,000 images per day. So at this kind of scale, the idea is we want to present to the client as many images. All these cars that we're pumping in, we want to basically put it on the web. We want to sell these cars. But we also want to make sure that the experience the customer has is uniform. We don't want to spoil the experience of the customer by presenting an ugly car. So what would you do? You hire a Photoshop technician, and who goes in there and removes with filtering and all that in Photoshop and makes the car as perfect as possible, each car. And this would work for a couple of cars, but at that volume, this is not going to scale. So to go from here to where we are now. As you can see, as we hired 100,000 Photoshop developers and put them in place, and they're sitting there real time removing the background. As you can see, obviously, something has changed. So if you don't mind me, let's go back to the previous one. I'm all about visual. Let's look at this, and let's go back to what we have now. This has been done via the capabilities that computer vision team provides in real time on the data stream of these images that we have. So what has happened here, as you can see, we try to provide this uniform experience for the customer. You can see these images, they were processed in real time and we will talk more about scaling, how it's done, the secret sauce behind the background removal. But you can see that the angle is very similar across time. You know, the coloring is similar. You know, they're zoomed in the right way. So a lot of the things that we take for granted as human beings are being done by the computer here behind the scenes. So without further ado, let's go ahead and share with you guys what are the teams that were involved in this process, because doing this at massive scale, it's not an easy task. So we have a lot of teams at CarMax that are participating in this journey, starting with digital merchandising capture, and every team has its own abbreviation, and sometimes they change, so it's sometimes hard to keep up. But this DMC, DMPD, and then us, computer vision. And so digital merchandising, basically they have the studios, they capture, they have the sensors, they capture the images, they upload to the cloud. Digital merchandising, processing, and delivery, they basically have the compute that basically orchestrate the delivery, orchestrate the capture, stitches things together, and then it dips into our team for the capabilities that we provide. Now, we do provide a few capabilities for these teams. Some of them are, obviously we cannot catch all of them and share with you today, but we will concentrate on background replacement, which is what we clearly saw what was happening behind the scenes. There's a lot more that's going on, but you know, we have background replacement, we have hero shot where you have a lot of different angles of the car, and we want to pick the best one for the customer to basically upload and present. We have quality analysis, we have region detection, we have color correction, and many, many more, but you know, due to lack of time, we're only going to talk about background replacement today, which is this. A picture is worth 100,000 words, or something like that. On the left and on the right, how do you get there without Photoshop at scale? So this is what we're going to show you guys today. And Sam has some cool demos for you. So what I'll do is I'll do a brief computer vision intro, and then we'll switch, and then Mr. Sam will talk about his brainchild a little bit later. But let's talk about computer vision, the genesis. So how do computers see? Believe it or not, in 1966, computer engineer at MIT Labs, Minsky, had a grant for summer to hire an undergraduate student to basically figure out, hey, connect this sensor to a computer and tell it what does it see. Obviously, at that point, he got the grant, so he got the money. He convinced the committee that it was an easy problem. He thought, how difficult can it be? And obviously, his student did not make the summer project, and it turned out to be the most difficult and challenging and arduous problem in computer science, which led to computer vision. So how do computers see? So basically, going from the CCD capture camera device, which can capture visual spectra or hyperspectra, doesn't matter, but in our case, let's capture the things that humans can see. It's really basically represented once the CCD captures it, which is a grid of transistors, transforms it into a computer. It's basically a matrix of numbers, which represents the intensity of the radiation that hit the CCD at that point. Okay? In this case, we just care about 3 or 4 numbers, RGB, which is the colors, maybe the alpha, and then basically you have this matrix, basically, which is given to a computer and say, okay, tell me what this is, right? Now, out of the gate in computer vision, there were really 2 kind of problems that you can consider. You present a computer a picture and you say, what is this? Is it a car? Is it a dog? Is it a fridge? Which seems like a nice recurring subject to make a recipe. Or you can say, given some kind of knowledge about what's going on in the picture, you generate me another picture. So one is, in a sense, classification, the other one is regression, okay? So if you look at these 2 images, they are, to us, obviously they're 2 different cars. We can look at it and we can tell. To a computer, not so easy, because let's say let's say the computer's looking at this matrix, which is the intensity of let's say the color, and it's basically around the back panel, it's just white and black. So it's basically, there's a saying, you can look at the elephant and if you look at its tail, and if 4 blind men can feel the elephant in a different way, and then they can never come up with it. So you need to have a uniform idea, okay, what is this? Instead of presenting a little picture of the matrix to the computer. So it's basically a difficult problem, right? As we know from starting from 1966. So what can we do? What has been done previously? So early days, this is still early days, and I apologize I try to avoid the mathematics, but just, so to keep it simple, what have been done is, you take this matrix, you take the thing, and you do some pre-processing in it. So basically what you do is you try to extract some information that can mimic the human behavior, for example, finding edges. That was done from the beginning, and ultimately what's driving this is an averaging process. So you take an image, which is your matrix, and you start at the top, and you basically take a little kernel or a mask, and you just drive it in the X direction and the Y direction, and you do some kind of averaging, right? What really won out, the best thing was weighted average. So basically, as you are at the spot, let's say IJ, you replace that intensity with the average intensity in that little kernel. And the farther the pixels farther away from that little kernel or the mask, the less weight they contribute. Remember, this is before neural networks. This is in the 80s. This is where convolution comes in. And what you do is you slide this little kernel, little window around, you average, and you get what you get. And then you try to make some decisions off of that, which turns out to be in 2D is a process of 2D convolution. It used to be, it's high computationally intensive, except that convolution in a signal space is actually a multiplication in a time domain. So you do with a fast Fourier transform with FFT, you can do some, this can be done, OpenCV does it very efficiently. But the problem here is that, if we go to the next one, is how do you detect the edge, even with all this technology? So what are you looking for? You're looking for a sharp discontinuity of intensity. So as you are going, whatever direction that you pick, let me rephrase it again. As a human being, we can look at an image and we can say, oh, the edge is perpendicular, or edge is this way, edge is diagonal. Computer just sees a bunch of numbers. So ultimately, you have to trace, start looking at your gradients in every direction and to see where's that discontinuity is and say, okay, this is an edge. Ultimately, you have an image and you have a kernel, which is a very simple kernel, in this case, 111000. So you average the row on top, don't change the middle, and then basically the -1. And then you slide this around, you get to the picture on the right, for example. This is just an example of a kernel filter. And then how do you determine if it's an edge in that direction? If it's within some distance, within some epsilon or t, then there's an edge. Otherwise, you don't have an edge. And this is just a hand-picked, let me say it again, it's a hand-picked kernel. That's one of them. The best one is the next one, which is Sobel kernel, which is applies convolution in two directions, X and Y, and this is what you get. You can extract some information, and then from that you have to classify, is that well, this is Lena JPEG, but it's like, is that a lady with a hat and stuff? It's hard to go from here to here. So as you can see, this is the state of the art, even up to 1999, 2000, it's some kind of OpenCV came out of there. A lot of algorithms are based on these. Okay, instead of looking edges this way, there's a lot of different things. And all they're doing is picking picking a filter. They pick a kernel convolution filter that does better at a particular job. So if you're detecting birds, you have some kind of filter that does good at that. For our case, the breakthrough came in with deep learning. So the accuracy of these methods these heavy mathematically based methods were 50%. It's like throwing a coin. If we go next, what made this really blew this whole thing out of the water is CNNs. What CNNs are really doing the same thing, except they automatically decide what kernel filter to pick. And while they're applying these convolutions, they find the best possible kernel for the problem. They apply the kernel. They reduce the two-dimensional data to a different space, which is a vector space, which is Simon's going to talk about from there. So basically, they take this thing, they extract the most important information with those convolution layers, project it in this vector space, and from there they hook in a classifier, and they can say a car or not a car. But in our case, this is kind of like, I'm keeping it generic. Let's go more concretely. How does this help us, right? And this is where Sam is going to talk about. Okay, so this is, as a summary for everything that I just said, forget about it. This is what I'm doing. We're doing a car. We extract doing some magic, now you know about convolutional kernels, but you hit it with something, it extracts you, gives you a vector, and then you pass that vector to another model, and it tells you, okay, this is a car.
Gotcha. So Yuri, what you're saying here is we can pass an image, right, and we put it through a deep learning network, which has convolutions and other things, right? And from that, we get a vector, right? And so for this example, for this car, and we'll see this for this example throughout the rest of the presentation, right? We have a 4-dimension feature vector here, right? And so this car, we run it through this feature extraction, and we get 3632, right? And so this is our feature vector. And then we can pass that, and then our classification network knows that this type of feature vector comes out as a car, right? And so we're going from a car to the vector to our classification. All right, and so that's our first type of network. And so remember, we have our first network that goes car to vector to classification. Now we're going to introduce a new type of network, right? And so this is generative modeling, right? So it's a generative adversarial network. And in our case, we use it for the creation of synthetic images, right? And we're not going to go into the deep history of what a GAN is, but you can think about the last network we talked about. We went from an image to a vector to a classification. From here, we're just going to go from that vector, and we want to go to an image, and a generated image here, right? And so in theory here, we have our vector 3632. We run it through a generative network, and we get a generated image, right? And then if we try again with that exact same vector, we should get that exact same image, right? And when it comes to GAMs, this is all we need to remember, for what we're doing here, right? And so just to summarize, right? So now we have these two types of networks, right? We have the network where we take the image, we go to a vector, and we go to a classification, and then we have one where we can go to from a vector to a generated image. But right, so these networks in our current time, we're not tied together in any way, right? So two separate types of networks, right? And so using this generative technology at CarMax a couple years ago, we said, all right, let's go and try to use this to generate photos of a vehicle, right? And so let's just go and try and generate a photo of this car. So what are we going to do here, right? And so our first step is we're just going to take a random vector. So let's go 3632, and let's run it through our generative network, right? And so we train this generative network with millions of photos of vehicles that we have at CarMax, right? And so we generated this photo, and this is what we got. We got a picture of a car. It's kind of facing in a different direction than our target and a different color than our target, right? And so we're kind of far off from the actual car we're trying to generate. So all right, let's get another vector, and let's generate it again, right? So we'll try 4277. Let's run it through our generator, right? And we get a new car here, right? So this time our car is facing kind of in the same direction. The shape's a little better, but there's still some differences between that and the target, right? And so let's go and let's try to repeat this 1,000 times and see how close we get, right? And so here we go, and we're just repeating that same step 1,000 times and trying to get closer and closer to our target photo here, right? And so we can see this happening. So at first, it starts its way off. It's changing the orientation of the vehicle, and it finally gets in, settles on the orientation, gets the shape a little better, and then tries to get the color as close as it can, right? And so we're pretty close here, but there's still some differences, right? And you can see it's not the exact image as the car on the left, right? And also, this took a lot of time to generate. And so if we want to use generative models at CarMax, right, we wanted to find a way we're able to get more accurate generations from real photos, right? And that was really our goal moving forward, right? And so at CarMax, we've tried to build a technology that would allow us to tie that GAN network and the encoder together, right? And so if we remember, so actually, here's an example of how a GAN is trained. And we're not going to go into details, super deep details about it. But right, so we have that generator network, which that's just the network we showed you previously in orange, right? It takes a vector and generates an image, right? And then what we did is we added that network we had on top of it, right? So we had that network that takes an image and then generates a vector and classification. We added that into our GAN training, right? And so we wanted to go to a space where we could go and we could take a real image, we could generate a vector from that image, and we wanted to regenerate, in theory, that exact same image through the generator model, right? And this would get us, allow us to basically represent our images in vector space, right? And so what we did here is, this looks similar to the previous slides where we had the two networks, but this time we tied these two networks together and we trained them as a single model, right? And so now, as part of our GAN training, our GAN loss includes the accuracy and loss of the encoder network that's being trained in real time with the generative network, right? And so now it's all the same model. We can go full circle, right? We can go from an image of a vehicle to a vector, and we can take that same vector and we can generate, in theory, a very similar looking vehicle to the actual photo we have, right? And so another thing about this, because we're training this generative model, as we change that vector, different things about this image are going to change, right? And so if we just take our 3632 vector, for example, and run it through a model, right, we get this photo here. But if we change certain things about the vector, we're going to get a different generated photo, right? And this is important because of things we'll explain later, right? And so because we've trained this model with pictures of vehicles, all different types of vehicles taken in different locations, this generative network is built to generate photos of vehicles, right? And so this is important. So this actually gets us in the space that allows us to change the image in ways we know, right? And so for this example back here, we just said, all right, we're going to work with a 4-dimension vector. In our case, to simplify it even more, let's just say let's look at this as a graph, right? And so we have 2 dimensions, x and y, right? We have this model that we've built with different vehicles taken, all different makes and models, different locations where these photos were taken. So for example, Yuri showed you a photo earlier of our search page, right, where we have all these photos of CarMax cars taken in photo studios, right? We also have locations around the country that don't have photo studios. And so we have a lot of data, of those 2 points, of different makes and models taken in photo studios and makes and models taken outside photo studios, right? And so we wanted to build a way to take a picture of a photo that was taken outside of a photo studio and make it look like it was taken within a photo studio, right? And so what we did in theory, so the vector space that we created within our generative model is about 54,000 dimensions. In this example here, we're working with 4 dimensions. And for this example, we have 2 dimensions here, right? And you can think about as we built this model, right, and we put in and we get the vectors for all of our outdoor images and then all of our studio images, all of our outdoor images should be clustered in a certain location in this vector space, and all of our studio images will be clustered in a certain location in this vector space, right? And then essentially what we can do is we can just find a slope between these 2 spaces in vector space, and you can think, all right, if we take an outdoor image that's going to be clustered in here and move it along that slope, we should be able to change the location that it appears like this photo was generated in, right? And so you can think about this. So you can think about this 2-dimensional space as the dimension that represents where a photo was taken. In reality, within our model, it might be 1,000 dimensions that actually represent where a photo was taken. But we can still do the same type of math, right, in a larger amount of dimensions. Right, and so here's an example of one of the first models we built in 2020 to kind of demo what this would look like. Right, and so we have a generated photo of a vehicle taken outside, and we want to make it look like a photo of a vehicle taken in a studio. Right, and so you can see here in this example what we're doing is we're actually just taking the vector space and we're moving it along the slope to try to morph it as if it was taken within a studio here. Right, and so we took that original vector space, we found the slope between where an outside image is and then where a studio image is, and we're moving that vector along that slope. And so that's why it looks like it's morphing from outside into studio. All right, and so that's one of the use cases we developed here. Another use case we thought is, all right, can we take a certain pose of a car? So here we're looking at a photo of a car from the rear. Can we make it look like it was taken from different angles, right? And so using that same technique, instead of saying, all right, we have a space for outdoors and we have a space for indoors, we're gonna have a space for every location or every position that we use in a 360, right? And so just taking the vector of this car from the rear, right, we can try to generate vectors in different orientations here, right? And so it looks like the car is doing a spin. And here, so this was actually our first model we built in 2020 to demo this. And you can see here, you can see kind of the model breaking down a bit as it's generating, right? And so you can kind of see features of the car changing here. And that's just because this, the vector space that represents what the car is doesn't identify, everything about the car, right? And so you can see here, like the wheels are changing a bit, the shape's changing a bit, the studio is zooming in and out. And that's because we are changing other things in the vector space when we're trying to transform it. So this is really cool because in theory, we've gotten to a position where we can take an image of a vehicle, right, get it into vector space, and within vector space, because we can generate the vector space for millions and millions of vehicles, right, we get the representations of the vehicles in vector space, right? And then we can change specific things about the vehicle within this space and regenerate the photo, right? And so if we don't change anything, we should be able to regenerate the same photo, right? If we change certain aspects in vector space, such as instead of taking the photo outside, we want it to look like as if it was created in a studio, right? We change that piece and regenerate it, right? And so that's the example here on the top. On the bottom here, we said, all right, we want to make it look like it was in a studio, and we want to change the color, right? And so we changed that aspect of it. And so now the car looks great. And what's really, so this is great. And so with this technology, we were issued a patent kind of in this way to change the vector space and regenerate images. All right. And so this is all really cool, innovative technology. But at CarMax, we're a retail company, and we needed to figure out, right, how can we leverage this technology in a way, right, that's usable for us and doesn't misrepresent the vehicle to the customer, right? Because what we're looking at here, like as we're changing, things about the car, right? You see things like the car itself is changing a bit, right? And as a company, right, we want to make sure we're representing the actual car, right? And so we found a way, and we said, all right, we want to adapt this technology to be used specifically for the backgrounds of cars. And so we said, okay, let's go and adjust this so we're only working on the backgrounds, and the car you're seeing is the car originally as it was captured, right? And so we did a couple of things. One, we updated the model to work only with backgrounds. And the second thing is we added another model into the system, right, that allowed us to capture where the car is in the photo, right? And so we take our original photo here on the left, we capture where the car is in the photo, we generate a new background for the photo for that same car, and then we put the car back in, right? And so this is really the tool, we call it like emulated Photoshop, where it's basically photoshopping a new background in for our vehicle, but we're keeping the vehicle itself the same, right? And the reason, like one of the big advantages of doing it this way is the background we're generating, right, is a background that's going to fit in with the car we're putting back into place. And so we know like the image should look realistic with the car being put in its new generated background, right? And so if we want to see an example of what that actually looks like in the steps, right, our first step is we're going to get the vehicle mask for a photo, right? And so we find out where is the car in the photo, right? So our next step is we go and we're going to generate a new background for the car. So this is using one of our later models. It's trained specifically for backgrounds. And so we try to regenerate the entire photo. And so what you're looking at here is it tried to regenerate this car, right? It didn't do a great job because it doesn't have much data on the car. But you can see it did, it did a pretty decent job, right? And we have kind of the logo there, the general shape is there. And so it did a relatively good job here, right? But then what we do is we put back in the original car, right? And so we put the original car in back on top. So now you're looking at a photo that has the generated clean background, right, with the original car. right? And so this is kind of how we adapted that technology today to be used in products we're using in our retail space. Awesome. So now we have a model that we can use and deploy to process our images. At CarMax, we're doing over 400,000 images a day. And so we needed to find a way to make this system usable for our consuming teams to run this at such a large volume. Is when we originally built this and demoed it, what we were doing, right, was we just had the Jupyter notebooks open and we showed like, hey, this is what we can do. And then people were like, this is great. Let's go and, can you do it 400,000 times a day? And we were like, all right, we'll work on that. And so doing that, we ended up building a system, right, that could scale efficiently, right? And so just to give you an overview of the space we're in and kind of how everything fits in, right? And so Yuri mentioned the teams involved that we work with, right? We have that capture team that's out there, capturing all these photos in different locations and uploading to the website. We have the team that's responsible once the image gets, online to make sure it's processed and then delivered to all the experiences we have on our website. So that could be like the search page or the car page. And then we're here, right? Our team has this box here, and we have all of our capabilities, right? And so we just demoed the background cleanup, right? But we have all these other capabilities that we also offer that our consumers can use when they're processing images, right? And so what we do is the processing team just goes and they call our system via an API, right? And so we need to build an API that was scalable in a way where our consumers could go and call and get these capabilities and make them usable for images, right? And so what technologies do we use for that? And so we're an Azure shop on our team, right? And so we use two main technologies, right? And so we'll go into a little more detail on what these are used for, but we use serverless Azure functions, right? And so this is the gateway, right? And so we have a single spot that our consumers will go and call and request data from, right? And then we route that to managed endpoints in the backend. So what this is we have individually deployed endpoints, right, that can scale for each of our capabilities, right? And so what does that look like on our end? And so this is just breaking it out, right, even more, right? So we have that consumer request, which those are coming from those teams that we integrate with, right? We have all of our individual endpoints available through APIs, right? But they call it just in one location on our orchestrator, right? And then we route these all individually to our backends, right? And so here's an example of some of the backends we have here. They're all individually deployed in our machine learning workspaces, right? And so we have our single API interface where our consumers can call, right? And then we have our individually maintained, deployed, and scaled backends, right? And a huge advantage of having this, right, is we can work on any of these models independently, right? And so we just went over what we call our Studio GAN model, right, that does our background processing. If we said, all right, we want to update a new version of this model or train a new model with new data, right, we don't have to touch any of these other models, right? We're just going to go and work with the Studio GAN model. We're going to train a new model and deploy it, right? And then our orchestrator will pick that up and get the latest model. So our consumer doesn't have any, doesn't have to see anything into our training and deployment. They just have the one interface they need to integrate with it, right? And so the last really big benefit we get out of having these individually deployed is that they can be individually scaled, right? If we have a consumer that calls our hero probability model 1 million times, right? What happens, right? That hero probability model can scale out, right? And so if we just have this on one VM and it gets called really aggressively, right? We'll scale out and say, all right, maybe we have hero probability model on 10 VMs, right, to handle all of that traffic. But all these other models can stay scaled down, right? And this is really important for us, and this was a really big break for us because all of these models are much more compute intensive than our traditional models that we're using in the machine learning space, right? And so before, if we said, all right, hero probability model is being called 1 million times, right? I need to scale everything up, right? That's not very efficient for us because one, all these models are very compute intensive and memory intensive, right? So we have to scale up all the models at the same time, right? We're going to have a lot of overhead that we're wasting, right? And so the ability for us to scale these up individually was a huge breakthrough kind of on our team and at CarMax. All righty. So that's how we scale things out. And just to summarize, right, what we talked about today. So the computer vision team at CarMax, right, we help ensure consistency at scale. When we're uploading 400,000 images a day, it's difficult for us to go and manually check and make sure all these photos, look the way we want to look, right? And so with computer vision, we're able to automate that process, right? And then we talked about that generator model that we've built that allows us to change the properties of an image, right? And so, you can get really advanced with this, change certain properties of the car. We've adapted this technology to kind of process and just change the background of our vehicles, right? And then we use Azure Machine Learning to actually deploy and scale these endpoints individually. So that's our presentation. Thanks, y'all, and I think we have some time for some questions.
Test. Super cool stuff. Quick side question. What does that cost us per day to do that?
Per day, at our current production scale, we spend about $200 a day to deploy all this and run it.
So that's super, super efficient, super, super cost effective. So again, thanks, Sam and Yuri. We'll take some questions. I hope you guys have some good questions for them. Put your hand up and I'll run a mic to you. I'll get the guy in the back first. If you could quickly introduce your name and ask your question.
Hey, my name is Vinod Swarnapuri. Hey, thank you both. You took this complex subject and made it very easy. That too, you started with the innovation where you started to deploying at scale. You covered a lot there. My question is more about the problem definition. Right? Here I was looking at both the things. One, you need to make it a consistent view of the car. Mm-hmm. At the same time, you want personalization, right? If you show the same, using the make and model, if you display the same image, you don't personalize one car with the other. How did you go about that? And you showed, even in your presentation, you showed both, right? You showed a pristine version, and you also showed that second version, keeping it as it is. I had a question on the second one, right? If you showed the car as it is, the image quality also matters, right? The lighting of the day. So it might also not represent the right car mm-hmm. because of the way the photo is taken. Yep. So I just want your thoughts on what went through your minds when designing this.
Yeah, absolutely. I think the biggest thing for us, and what was really big with our engineers when we were talking and working with our product teams, right? We want to make sure that we are not altering the car in any way, right? Because that leads to big issues, right, down the line. Right, and so for us, that was really important. That was a showstopper for us. So we needed to make sure we adapted for this technology in a way where we could still utilize it, but maybe in a way that allows us to, still keep the car the same, right? And so that's where it was really important for us to add in that second piece, right? That masking model. And we said, all right, we're just going to mask the car, we're going to change the background, and then we're going to put the original car back in, right? And so that was kind of what we developed. And if you look in, if we looked at when the car was transitioning, right, you see the one things we don't get with the way we do it today, right, is what this model has the ability to do is, right, when the car is taken outside versus inside, right, the way the lighting on the car reflects off the shiny material, right, is going to change, right, when you take the car inside versus outside, right? The color might change, the shadow might change. What this model does really well with the way we developed it, right, is it makes sure it recreates those shadows, right? And so we found those shadows are a good way to making sure the car feels grounded when you're looking at it. And it's nice because the shadows are still part of the background, but the car itself, we don't have to touch. Things like reflection, on the car, right? Those are going to be vastly different when we take a car outside versus inside, right? And so today we use this technology to correct our photos taken in a studio, but we have yet to use it for cars taken outside and make them look like they were taken inside. And so that's something we're not doing today with this type of model, but it's something we're kind of looking to, and we have ideas about how we're going to do that in the future.
And we also have other capabilities like color correction and other capabilities that we provide that are not generative. We did not speak too much about them, but there are other things that we can do. Some of them are not using deep learning at all. They're just OpenCV, capabilities. But
good question. Another question? I saw some hands. Whoever's closest to me wins. Who is first? I'll go with her. She's smiling. You gotta smile.
Hey, I'm Sandy. I was wondering, for the masking of the cars, are you using some sort of feature detection to find the line's edges, or is there sort of like a generalization where you are sort of looking at sort of the center area and just abstracting that, like, all right, this chunk is just going to be masked? Yeah, I guess that's the question.
Yeah, no, that's a really good question. And that gets into, so that's also a really complex problem that we're still like, and that's one of the problems we continually solve on this team, right? We want to be able to tell exactly where a car is in image, pixel by pixel, right? And so we have a specific model for that. It's like a UNet segmentation model that we use to pick out where the car is in the specific image, right? So that's a deep learning model that we train and we keep up to date. That's part of this process, but it's really important because the better that model is, the better our generation is gonna be, and the better the image is gonna look. And so that's like one of the models we use to power the system. But yeah, it's a deep learning model, and then we have some other processing on top of that that's not deep learning to make sure we can identify where the vehicle is in the photo.
And to add to what he's saying, the UNet by itself is off shelf, so it's trained on a lot of other images. So to make it better, we're trying to use like transfer learning and basically work with some other companies that help us label things better. So we can actually only pre-train like the last layer, use all the power that's already been learned, and then detect a car. Because we know we're dealing with cars. We don't care about birds and stuff. So only for the cars, we can do better.
Next question's from a CarMax associate. It's not loaded.
Yeah, thank you. Great presentation. My question was about the 360-degree, I think it's a GAN or whatever model it was.
Yep.
I know that on the CarMax website, there is right now a 360-degree view. I'm not sure if that's a later version of what you showed, but when you're evaluating the, I guess, accuracy of that generation, like what is the kind of metric or way you determine that as you go through the 360 degrees that it looks similar enough that it's not like an issue or like misleading?
Yeah, absolutely. And the thing I'll say is like with this, when we're looking at it, if there's one pixel that's off, it's wrong, right? And we shouldn't be showing it. And so, I'll say that. And for the 360 generation, it's really hard, right? Because if you're looking, right, at a vehicle from the rear, right, you don't know if there's a scratch or dent on the front of it, right? And this model doesn't know it, right? And so what it's doing here, essentially, right, is looking at the rear of this car. And it's like, all right, here's a rear photo of this car. Have I seen pictures of cars that look similar to this? What do these cars look like from the front, right? And so it's kind of doing it that way. But right, if there's one pixel off, right, it's wrong, and so we shouldn't be showing it. And so the 360s you see on the website today, right, those are actual, so we take 61 photos of a vehicle to make that spin for you. So those are the actual photos. And then when we evaluate like a 360 like this, right, we could really use this technology. Like if you wanted to add, make the transition smoother, you could make me do photos in between where it's like, all right, I have this vehicle, this picture of the back of the vehicle. Maybe I could generate one position over, but it doesn't know anything about the front of the vehicle. Right, and so,
or if one is missing, for example, sometimes the capture team don't capture all the things. One is missing or one is corrupted.
Yep.
We can use this technology.
True. Yeah. If one is missing. Yeah. Absolutely.
Yes. Former associate. Yes. Also not planted. So when you're describing the GAN system, is it really as simple as just the 4 vectors and like that's it? Like that's all you put in, then like all the. Okay.
Yeah, really good question.
I simplified like for this, or if it is that simple, but.
Mm-hmm. Yeah, so we use the 4 dimensions to simplify it for y'all. Yeah, of course, 4 dimensions it doesn't encompass half the information, or like 1% of the information we need in these images. So the transitions you saw, that vector space, that was 54,000 dimensions.
All right, who's next? We're standing between you guys and lunch.
Thank you for the presentation. I'm curious, how do you guys control for quality, like the images that are getting taken and sent in, and then ensuring that like when you're trying to draw the bounding box around the car that you're not chopping off half the car before it's presented?
Yeah, those are really good questions, right? And because we're doing this, right, at so much scale, we can't manually review every image, right? And so what's really nice is, so all of, like most of the photos you see, of the 400,000 photos we capture a day, right, 90% of those photos are going to be taken by essentially like a robotic process, right? The car gets driven into a photo studio, associate hits a button, the car spins and photos are taken, right? So that's really nice because those images, you know, are pretty consistent. We have processes that we've developed for other associate taken photos, right, that we didn't talk about today, like those processes, but we analyze, so our team analyzes associate taken photos for consistency and quality, right? And then the associate will go and get a report and say like, all right, how am I doing compared to other associates, you know, at CarMax, right? And so that's a whole process that we have developed for associate taken photos. And so, and that's done with a lot of, you know, hand label data, what's good, what's not, right? And then in terms of making sure we don't chop off the car when we're masking it. So we're not going to be perfect, but right, so what we do, like we have a very rigorous process that these models go through before they actually make it in front of consumers, right? And so like we have a really big review process. We have a lot of data that we need to run the model over and make sure it does well on before that model gets approved to go for the website. But because we're not monitoring every photo that we process, right, stuff's going to go through. And so in our training and validation process, we need to have a lot of steps to make sure that what we're putting in front of consumers is good enough.
One more question before lunch. Anybody? Aaron, read the book. Oh, that's my always answer for you.
Yeah, do you have a book? No, it's kidding. So what are the requirements you guys set for yourselves in terms of like generation time, right? Because I mean, what's the time that like your requirement in some sense for like from it hits the API to it's out on the website?
Yeah,
I mean,
yeah, absolutely. And that's something we work, you know, really hard with our, you know, with the teams we work with in photos, right, to make sure that we get the photos to the website in a timely manner, right? And so, like for us, when we built out our API system, right, for this generation model, we wanted to make sure that we could get every photo out in 10 seconds or less, right? And so what we find with this model is I think we average around 7 seconds is where we are, and we're pretty happy with that from a performance standpoint.
Great questions. Another round of applause for Sam and Yuri.
Thanks, y'all. Appreciate it.
Thanks, guys. Great job. Lunch. So if you're an attendee, you get free lunch. You get an hour to socialize, network, go see our vendors and companies that are out in their little vendor hall right here. Appreciate everybody. Thank you.